Okay, so today we're going to talk about the number e. What is it? 3, 19, 18. All right, so the number e comes from this guy, this French mathematician, not Euler, which I thought it was Euler. I did all the way through my freshman year of college, and I was starting to major in math. I thought for sure this guy's name was Euler, but it turns out it's really like Euler. That's really the way you'd pronounce it, but this is that's the correct way to spell it. So it's Euler's number, and Euler's number is the number e, okay? How do we find the number e? So before we do a whole lot, the number e comes from this equation, okay? So what we want to do is, as the value of x gets bigger, we get closer and closer to the value of e. In fact, if we can make the number so big that it's infinity, we would get exactly the number e. So let me go ahead and do some of this on my calculator, okay? So before I do anything, the number e is on your calculator. It's down by the division symbol, so see if you can find it. So I go and I hit the number e. Everybody find the number e? Everybody find e? Okay, it's down by the division symbol, right? Yeah. Yeah, second division, and there is the number e. Except for that's not exactly a number e, because e is like pi. It's just like pi. It keeps going, okay? So this is the most we're going to see on a calculator. But it's an irrational number, like e is. So we know that e is an irrational number. Irrational numbers are those numbers that are decimals that never repeat. They go on forever, right? So let's see if we can get close. So if that is close to the number e, watch what happens. Okay, if I go parentheses, 1 plus 1 divided by 10 to the 10th power, I get about a 2.5837, okay? So if I plug in 10, I get about a 2.5937, blah, 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 okay? Not quite the number e yet, but closer, okay? So let's let it be even bigger, okay? Let's go to 1,000. So I'll go, okay. I'll go 1 plus 1 divided by 1,000 to the 1,000. And this time it's a little bit closer to what the value of e is. So I get this time about 2.716923, blah, 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 okay? It's getting closer to the number e. Okay, then if I get even bigger to the millionth, I go parentheses 1 plus 1 divided by 1 million, so 1, 2, 3, 4, 5, 6 zeros to the 1, 2, 3, 4, 5, 6 zeros. Hey, now this time we're getting pretty close to the number e, right? So if I compare this to the number e, they're pretty darn close, aren't they, right? And then, so then we'll go to the billionth. So if I go parentheses 1 plus 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros is the billionth to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the number e. Again, now this time they're really, really close. So what happens as n gets bigger and bigger, as it approaches infinity, we get to the value of e. So the definition of e. This is the definition of e. So if I said, what is the definition of e? It's the limit. The limit means to get close to something. In calculus, we use the word a limit to describe things that we're going to get closer to that we can't get to, okay? Closer to that we can't get to, okay? So the word limit in calculus means let's get as close to something that we can't get to. Well, you can't get to infinity. So we say as n approaches infinity, we'll get this number e. 2.718, blah, 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 blah. But the exact value of e is just the number e, okay? Now, why do we need to learn e? Well, it turns out in nature, like either when you get sick or a half-life problem, things grow at this rate. Not necessarily by doubling or tripling, but things grow at this rate in nature. So if you got bacteria that's growing in a petri dish, they're going to continuously grow, okay? And the definition kind of shows why that works, okay? And so because the number e is the number described in nature, then its log function, its opposite, is called the natural log. Okay? So when you see this ln, and that's in your calculator also, the ln is the log with base e, okay? And the reason they call it ln is because it's the natural log and it's the rate at which things grow in nature. I'll say that again. Okay, when you take e and look at its log, it's going to have a log of base e. Okay, things grow in nature naturally at that rate, so log of base e we use as, we say it's the natural log. I know it's ln, but it's the natural log because it's the rate at which things grow in nature, okay? Now if I look at my calculator, sure enough, there's a e to the x button right there, and right with it is the ln. So when I told you that there's only one base in our calculator, I kind of lied. Didn't do it on purpose. Yes, I did do it on purpose. I did lie on purpose. Because really there's base 10, right? Base 10, which is what we count in. And then there's this ln, which is log of base e. So we have two different logs in our calculator with two different bases. Okay, we're going to use this one today. We're going to use the natural log today. Okay. All right. Let me back up. Example 2. Let's graph this. Okay. So let me put on my calculator. Show you what it looks like. I'm going to go y equals, clear that, clear that. I'm going to go then e to the power of, and that's down by the ln, to the power of x. Let me change my window slightly. So I'm going to graph this. Let's go 0 to maybe 5, and we'll go maybe negative 10 to 5. I kind of know what it's going to look like. Okay, now let's make that negative 5 to 5. Let's graph this. Oh, I got the wrong window. My bad. I got the wrong window. Let's go negative 5. Let's make this a 10. There we go. That looks like an exponential, doesn't it? And I do know it has to go through at 1 because anything to the 0 power, even e, anything to 0 power is always 1. So my graph looks something like this. Looks exponential, right? This graph is going to have a horizontal asymptote at y equals 0. And an asymptote is a borderline. It's a borderline to where the graph will approach but never touch, right? This graph's getting closer, closer, and closer to 0, but it'll never get to 0. It's like that half of a half and half of a half of a half, and you never get to 0, right? And that's why you have this boundary line that says you're not going to get there, okay? Now, if we want to look at the log, let's see here. I do know that these two are inverses. These two are inverses of each other, okay? So if I inverse this, then we'll just switch the points around. This is the point at 0, 1. So its inverse would have a point at 1, 0. With inverses, x's become y's, so this horizontal asymptote would have to become a vertical asymptote, because inverse, we just switch the x and y. So if y equals 0, we'd have an asymptote at x equals 0. And the graph, we put it in our calculator real quickly. I want to put it in there. If I put the graph in the calculator, I'm just going to go natural log of x. And I'm going to fix my window. It goes 0 to 5. And we'll go negative 5 to 5, and we'll graph this. Okay, and it looks like that. Okay, now, if I look at my calculator, it really looks like it touches here, but it doesn't. It looks like it touches here, but it doesn't. We know it doesn't. It gets closer and closer and closer to that, but it never touches, okay? So it's going to look like this. And that's the natural log graph. One of the things we know for sure, that we can't take the natural log of 0 because it never touches 0, does it? Can't do natural log of 0, so that's undefined. And we can't do the natural log of negative numbers because there's no negative values over here, right? And you can try it in your calculator, you get the same problem. And that's got to be undefined, okay? So on my calculator, if I happen to make a silly mistake and try and take the natural log of 0, guess what it's going to tell me? Yep, doesn't like that, does it? Nope. Doesn't like that at all. Quit. Or if I try and take the natural log of, say, a negative number, yeah, it doesn't like that either, does it? Nope. So you can't do either one, all right? Okay, let's keep going. So now, let's go to example 3. We want to solve for x. Boys listening? I know you are. So normally, what we learned last week is if you have x in the exponent, we want to float it down. We take the log of both sides. Remember that? Take the log of both sides, log of both sides. But this time, let's not take the log. Let's take the natural log, because the natural log of e is equal to 1. And we want to keep that in mind. So instead of the log, because we get log, how about the natural log? With e, use the natural log. So with e, don't use log, use natural log. So it's natural log of e to the x equals natural log of 12. And we learned that when we do the log or natural log, we like to do that because it will float the exponent down, right? Remember that from last week? So the exponent comes down, and we get x ln of e is equal to ln of 12. Now one definition is this. The natural log of e is always 1. Okay? Up here, the natural log of e is always 1, okay? So I'm going to have x times 1 equals the natural log of 12, right? And then what is the natural log of 12? I don't know. Well, let me calculator do it, okay? So I'm going to take my calculator, and I'm going to go ln of 12, and I get finally my answer about 2.4849. 2.4849. Okay, does that seem pretty easy? So with e, don't use log, use natural log. With e, don't use log base 10, use natural log, which is base e, okay? All right, example 4. All right, I want to change this to exponential, but I don't know what the base is. It's e. So the base is hiding, but it's e. So let me rewrite it. I wouldn't normally do this, but for right now, ln is really log base e. Okay? ln is really log base e. Now, again, I wouldn't write this normally, but it does show that ln is log base e. Okay, now I'm just going to go exponential form. So I go e to the 3 equals x, right? So we're going to go e to the 3 equals x. And what is e to the 3? I'm going to use my calculator. So I go e to the 3rd power. About 20.086 maybe, about 20.086. Not too bad. Okay, example 5. All right, simplify. Well, one of the things I see right off the bat is this is an exponent. That's a log. So I can float this down, right? Because logs allow us to float the exponent down. So I'm going to rewrite this, bring down the 3.2. I'm going to go 3.2 ln of e. Oh, wait a minute. ln of e. Wait a minute. Hold on. ln of e. ln of e. ln of e. Ln of e is equal to 1. So that means I've got 3.2 times 1, which is just 3.2. And you could have done that on the calculator actually, but you know, you could have gone straight to Mr. Davis. It's just numbers. I could have gone ln e to the 3.2, and sure enough, 3.2. How's that, Jamie? Right? That works. Okay, number 6. Am I going too fast, or am I okay? All right, number 6. So I'm going to do something a little bit different. I'm going to bring this 2 back in as an exponent, okay? Now, normally I wouldn't do that, but since I want to solve for x and simplify this thing, I'm going to rewrite this as an e to the ln of x squared, okay? Now, why would I want to do that? All right, let me circle this for a second. Let me slide my paper all the way up. Hey, here's a rule we haven't talked about, and that is if you have an e to the natural log of x, these two cancel each other out, and you're just left with x. Because they're opposites of each other, aren't they? Inverses. So then I go back to this. If these two cancel each other out, you're just left with an answer of x squared. Thumbs up so far? All right. Turn the page. Okay.
So, Mr. Davis, how do you, make it, how does 2 become an exponent of x? Why can't you do that?
Because normally if that exponent you brought it, so it got brought down because it's a log, but it brought it back in, okay? Okay, so go back to this.
Oh, I see. So it's, I get it.
I just brought it back up, right? Okay. Yeah, Stella, I can prove these if you want me to later, okay?
You know, I get it, because it's just like the log. It's the same rule applied. This is the log, and that's why. But
Yep.
how is the e there? How is that the exponent?
This is a log of base e, so we learned that before. If we had base to the log of the same base, they cancel each other out. But I can prove this to you later, okay? When I'm not recording. Okay, turn page. So now, boys, you listening? So easy question, but we got to pay attention. So in banking or in anything, if something, you ready? If something grows continuously, okay? Guys, so if something grows continuously, then what happens is you have to use this E because it's a natural phenomenon, okay? Something grows continuously, it'd be growing like in nature, so we have to use the E value. So in banking, they call this the PERT formula, but it's principal times E, R is your interest rate, and T is your time, okay? So we're going to use this formula to find out how much money total we're going to have after 5 years, okay? And boys, you're not talking, are you? So let's do it. So I want to invest $10,000, which I'll put in for P, 6.5%, which will make 0.065, and for 5 years. So let's do it. A of 5 is equal to 10,000 times e to the 0.065 times 5. I'm going to make sure that when I use my calculator that I use parentheses because I want to make sure the 5 is in the exponents. That makes sense. The 5's got to be in the exponents. So I need to make sure I use parentheses in my calculator. So I'm going to plug that into my calculator. I'm going to go 10,000. And I'm going to use my E button, which is by the 4, to the 0.065 times 5. And I get about $13,840. Now this is total. This is interest and your original investment, okay? That's your $10,000 plus your interest. So your total amount would be $13,840.30. Okay, pretty easy. You can do that on the quiz on Wednesday. As long as you have your notes, it's not too bad. Okay, now, example 8, though, is a little bit different. It doesn't compound continuously. It compounds quarterly. So anytime something's compounded, if it's compounded quarterly, 4 times a year. So what the bank does is after 3 months, it gives you a little bit of the interest. Now that's a good deal because then you've got some money in the bank that the bank gave you. So when they compound it again, they compound your money plus a little bit of the interest, okay? So then when they compound it again in another 3 months, you get interest on your money plus interest on your interest that the bank already gave you. So it's kind of a good deal. So quarterly means 4 times a year. So in this example, N is going to equal 4. Okay? If it's semi-annually, and it would be 2. If it's monthly, and it's going to be 12. You got it? If it's daily, then it's 365. Okay? So here's our formula. P, which is the principal. R, which is the interest rate. In this case, it's 0.07. Okay? And T is 5 years. So let's plug it in. So let's go A of 5 is equal to, where you're going to do the same $10,000, okay? $10,000. 1 plus 0.07 over 4 to the 4 times 5. Again, I want to make sure I use parentheses for my exponent because I need the 4 and I need the 5. I need both the 4 and the 5 to be in the exponent. Okay? Or you just make that a 20 and make it easy for yourself, right? Just make it a 20, make it easy. But I'm going to keep it there so I can show it. Okay? So let's find out. After 5 years, total amount of money. So I'll use my calculator. I'm going to go 10,000. Parentheses 1 plus 0.07 divided by 4 to the power of parentheses 4 times 5, or 20, right? But I wanted to show the parentheses. Okay, boom. $14,147.78 is how much we're going to make in 5 years total. That includes my original 10,000 plus the interest, all right? So let's put that answer down. 14,140.
Making more than that, though?
Oh, that's pretty good interest, 7%.
What, I know, I mean, like, they say it's for compounded continuously, that means every year, right?
Right.
6.5%. But
Yeah.
this is compounded quarterly, so it means you make 7% interest every quarter, correct?
Right.
So that one's,
So
you'd
what?
be making more interest
Right. So
four
what?
times a year?
I'm glad you're asking this question. So the question is, this one's compounded more often. And why is this a higher investment? Because the interest rate always trumps it. So anytime you do any banking, Jerome, it's the higher interest rate that you want to look at always. Because this one's compounded all the time.
Oh, that one's compounded
All the time.
Oh, I
This
thought
should
it
be
was every
more.
year.
No, this compounded all the time, continuously.
single day.
Every single day, every single moment, in theory, every single moment. So you'd think this would be more, wouldn't you? But the interest rate is not as much.
No, I thought that would be, I thought the second number would be a lot more, because I thought the first one was every year.
No,
I
it's
guess-
it's that word continuously, right? Whereas you'll see, they'll say annually if they mean once a year,
So
okay?
continuously, how do you earn?
Oh, the credit card so what happens in the real world is you will never get this, but the credit card companies would like to charge you this. Now, they give you a daily interest, right? Some credit cards do, which is crummy, but it can happen. Okay, last but not least, okay? A paleontologist, okay, uncovers a fossil of a saber-toothed cat in California. He analyzes the fossil and determines that 15% of its original carbon-14, which has a half-life of 5,730 years, okay? Now, here's how it works, okay? We're going to find out what we have to do. So N of T means the amount over time. This is the amount over time. N0 is the original amount. That's the original amount. So if we're doing a percentage problem, right, this is always going to be 100. So when you're alive, and right before you die, you have 100% of your carbon-14, right? I mean, you haven't died yet, right? And then you decay. Sounds gross, doesn't it? Anyway, so this number will always be 100, okay? And then E is how something grows or decays continuously. And then you get this value K. And the K is different for every substance. I mean, this is carbon-14. You can measure it with uranium. It's quite a bit more quicker. It's more quickly. Plutonium. Some of those have much different numbers, okay? So what we have to do is find K first. This is how it works, okay? We want a half-life. That means like 50% is half of our 100%. Okay, does that make sense? If we start with 100%, then after so many years, we have 50% of it left. Okay? Times our E to the negative K times, well, how many years does it take to go from 100 to 50? It takes 5,730 years. Okay, now I'm going to back up so you can see I'm using my formula. Okay? Always remember, N of 0 is 100. Always remember, N of 0 means 100. And why don't they write 100 in there? Well, the scientists don't. But I want to make sure when you take Stubbs class, you know where it comes from, okay? So, when we're alive, we have 100% of our carbon. Then we die. And then after so many years, 5,730, we only have 50% of our carbon. So what we want to do is find the rate, that's the K, at which it decays. So let's solve, okay? First step, divide by 100, divide by 100, right? So I get 0.5, divide by 100, right? Divide by 100. I get 0.5 equals E to the negative 5,730 K. All right, I'm just going to solve for K. I got to find K. Divide by 100, divide by 100, okay? I want to float the exponent down. How do I do that? Yeah, it's ln. So let's take the log, but let's take ln specifically because of E. So I'll take the ln of 0.5, right? Equals, and I'll float it down. I'm going to skip a step. Negative 5,730. And we'll have the ln of E, okay? I skipped a step. Yeah, thanks, Jerome. Thank you. Glad you guys are here. Make sure I don't make too many dumb mistakes, huh? Now, hold on. Before I do anything, I'm going to flip the page, right? Okay, everybody got this? Hey, what's ln of E? All right, so I'm going to change that. That becomes 1, right? So really, I have ln that becomes 1 of ln of 0.5 equals negative 5,730k, right? Because the ln of e is 1, I don't need that. And then to solve for k, I'm just going to divide by 5,730, divide by negative 5,730, and I'm going to use my calculator, okay? I use my calculator, find out what that is. I'm going to go ln 0.5 divided by negative 5,730, and I get an answer of about, now I get this e thing, I got to be careful. So in scientific notation, this is not a negative, this is not a negative, I'm just going to move this decimal 1, 2, 3, 4 this way because the e, scientific notation, so I move this decimal 1, 2, 3, 4. So k is equal to the value of 0.0001209, okay? Now, let's use that number to make our equation. So let's make our equation for carbon 14, right? So we're going to take and go n of t is equal to 100 e to the negative 0.0001209 t, all right? So I'm going to go ahead and highlight my formula. Here's my formula, okay? Here's my formula. And I just put everything in, okay? I know n of 0 is 100, right? I put in my value of k. Now I can use this formula to go ahead and find out how old is this tooth? How old is this bone? Well, let's check it out. I know that there's only 15% of it. So I'll put the 15% right there, the amount over time, right? So let's put 15 here equals 100e to the negative 0.0001209 t. Right, how am I doing? All right, it's a hard problem, isn't it? But we can do it. Okay, now let's solve. Divide by 100, right? Divide by 100, divide by 100, and I got 0.15 equals e to the negative 0.0001209 t, right? Let's float down the exponent, but how do I float down the exponent? How am I going to float down this? Let's log it, but better yet, ln, right? Let's log it. Logarithms help bring it down. Let's specifically use the ln. So I'm going to go ln of 0.15 equals negative 0.0001209 t ln of e, but ln of e is 1, so get rid of that, right? ln of e is 1, right? That equals 1. So now let's divide, and I'll have ln of 0.15 divided by negative 0.0001209 is what t is going to be, and I need my calculator, don't I, right? Got to have my calculator. So I have ln of 0.15 divided by negative 0.1231209.
Is it negative?
Because it's decay. Because it has to be negative because it's decay. So my answer is about 15,691 years old. That's how old that tooth is. So about 15,691 years old. Years old. That was a good problem, huh? Okay, I did make one small adjustment for second period. I made this evens here. Okay, I did make that evens, okay? We highlight it. So here is our assignment.
Something went wrong.
Not on mine. I'll check this. Let me stop the recording.